clear night, the Milky Way can seem almost motionless. Its pale band holds the same familiar curve across the sky, while the constellations rise and settle with the turning Earth. Nothing in that view reveals the larger motion carrying our galaxy through space. Yet, nothing around us is truly at rest. Earth moves around the Sun. The Sun circles the center of the Milky Way at hundreds of thousands of miles per hour. The Milky Way and Andromeda move within the local group, accompanied by dozens of smaller galaxies, and the local group itself moves through the universe at roughly 600 kilometers each second, relative to the cosmic microwave background. That last motion is the one that opens tonight's story. The cosmic microwave background is the oldest light we can observe, released when the young universe first became transparent. It arrives from every direction, forming a faint reference field behind the galaxies. When astronomers measured it with enough precision, they found that it was slightly warmer in one direction and slightly cooler in the opposite direction. The difference is small, but its meaning is clear. We are moving. It is something like the change in sound heard when a vehicle approaches and then passes, except here the signal is light spread across the entire sky. The pattern gives astronomers a cosmic frame of reference, a way to measure the motion of our local galaxies against the distant universe. Once that motion was known, another question appeared. What was causing it? Gravity offers the broad answer. Matter draws matter. Galaxies gather into groups, groups into clusters, and clusters into long filaments and walls. Between them lie enormous regions with far less matter, places whose emptiness can also shape the direction of cosmic flow. Across hundreds of millions of light years, these uneven distributions create a gravitational landscape. Our galaxy is moving through that landscape now. During the 20th century, astronomers began mapping the velocities of nearby galaxies. They found that many were not simply following the smooth expansion of the universe. After the expected expansion was subtracted, a residual motion remained. Galaxies across a wide region seemed to share a flow toward the southern constellations of Centaurus and Norma. The inferred destination became known as the Great Attractor. The name suggests a single hidden object, perhaps one immense cluster, or an unseen concentration of dark matter. But the real picture has never been so simple. The Great Attractor is not a giant body waiting in one exact location. It is a name that grew from measurements of motion, a way of describing a region in the local cosmic web where many gravitational influences appeared to converge. Part of that region lies behind the crowded plain of the Milky Way, where stars, gas, and dust obscure distant galaxies in visible light. For years, astronomers could detect the motion more clearly than they could see the structures responsible for it. Even now, the answer continues to widen. The Virgo cluster contributes. The Hydra Centaurus region contributes. The massive Norma cluster lies near the traditional Great Attractor direction. Farther away, the Shapley concentration adds another deep pull. Nearby underdense regions may also help guide the flow by offering less gravitational resistance. In other directions, the Milky Way's motion is not the work of one hand. It is the combined result of a landscape made from clusters, filaments, dark matter, and voids, each adding a small part to a movement that crosses scales far larger than any galaxy. Tonight, we will follow that movement outward, beginning with the oldest light in the sky, and ending among the immense structures that shape the paths of galaxies. The stars above may appear fixed, but the ground beneath that view is already in motion. The first clue is not found among nearby galaxies. It is written across the microwave sky. The cosmic microwave background surrounds us with radiation released when the universe was young enough for light to begin traveling freely. In nearly every direction, that background has almost the same temperature, but almost carries the entire measurement. One side of the sky is slightly warmer, while the opposite side is slightly cooler. This broad two-sided pattern is called a dipole. The warmer direction is the direction in which the solar system is moving. Light arriving from ahead is shifted to slightly higher energies. Light arriving from behind is shifted slightly lower. The difference is only a few thousandths of a degree, yet it is stable enough to serve as a speedometer placed around the whole observable sky. There are smaller motions nested inside it. Earth travels around the Sun. The Sun follows its path through the Milky Way. The Milky Way moves within the local group. Astronomers separate these layers with careful corrections, removing the motion that is already known, so that the deeper movement can be measured. Earth's annual orbit adds a smaller dipole that changes predictably through the year. Because that orbital speed and direction are known with great precision, the changing signal also helps astronomers test and calibrate the instruments, measuring the larger solar motion. Planck measurements place the solar system's speed relative to the microwave background at just under 370 kilometers per second. After accounting for the Sun's motion within the Milky Way and the Milky Way's movement inside the local group, the motion of the local group comes to roughly 630 kilometers per second. At that speed, the local group would cross the distance from Earth to the Moon in a little over 10 minutes. Yet there is no wind against the planets and no sensation of acceleration beneath the night sky. Earth, the Sun, and the nearby galaxy share so much of the same movement that the motion becomes visible only when compared with something far beyond them. The microwave background provides that distant comparison, but a direction of travel is not the same as an explanation. A compass can show which way a boat is moving without revealing the currents beneath the water. In the same way, the dipole shows the motion of our cosmic neighborhood, but it does not identify every concentration of matter responsible for it. To find those influences, astronomers must measure how other galaxies move. That task begins with redshift. As the universe expands, distant galaxies generally recede from one another. Their light is stretched toward longer wavelengths, and the amount of stretching gives an observed recession velocity. On large scales, the farther a galaxy is, the more expansion usually contributes to that recession. Gravity adds a second motion. A galaxy may be falling toward a cluster, moving away from a void, or traveling with a larger stream of neighboring galaxies. This local departure from smooth expansion is called peculiar velocity. The word peculiar does not mean strange. It means the velocity belonging to the galaxy in addition to the general expansion of space. Redshift alone cannot separate the two. Astronomers also need an independent distance. If they know how far away a galaxy is, they can estimate how quickly cosmic expansion should be carrying it from us. They then compare that expected motion with the velocity measured from its spectrum. The remaining difference is the galaxy's motion through the gravitational landscape around it. The arithmetic sounds simple. The observations are not. Galaxies do not arrive with their distances printed beside them. Astronomers build those distances from patterns in light. A pulsating star can reveal its true brightness through the rhythm of its variation. The brightest red giant stars can mark a recognizable stage of stellar evolution. The rotation of a spiral galaxy can be compared with its luminosity. The internal motions of an elliptical galaxy can serve a similar purpose. Certain supernovae provide another calibrated light source across larger distances. Each method has its own range and uncertainty. Some work only nearby. Others reach farther but depend on relationships that must be carefully calibrated. Dust can dim a galaxy. Viewing angle can alter its appearance. A cluster may contain many galaxies moving around their shared center, making one member a poor guide to the motion of the whole. So the measurements are gathered in large numbers. A single peculiar velocity can be uncertain enough to point in the wrong direction. Hundreds begin to reveal a tendency. Thousands can trace streams. Galaxies are often combined into groups so that their individual orbital motions partly average away, leaving a clearer estimate of how the group itself moves through space. Modern catalogues join many distance methods into one common scale. They do not turn the local universe into a perfectly known map. The uncertainties remain substantial and coverage is uneven. But repeated patterns survive the noise. Some galaxies move toward us a little faster than expansion alone would predict. Others recede more slowly. On the far side of a dense region, the pattern may reverse, with galaxies falling inward from the opposite direction. When many such measurements are placed in 3 dimensions, motion begins to outline mass that cannot be weighed directly. This is one of the more patient forms of astronomy. The objects being studied may lie tens or hundreds of millions of light years away. Their spectra are gathered one at a time. Their distances are calibrated through generations of work on stars, galaxies, and exploding suns. No single observation reveals the current. The current appears only after many measurements are allowed to support one another. By the late 20th century, those measurements were showing a coherent flow in our part of the universe. The local group was not moving alone. Other galaxies and clusters shared part of the same drift, and their peculiar velocities and their peculiar tools pointed toward a region of the southern sky. The name Great Attractor grew from that flow. It did not begin as the name of a photographed object. It began as an inference. Somewhere in that direction, the distribution of matter was altering the smooth expansion of nearby galaxies. The motion came first, the map of the cause came later, and the place where astronomers most needed to look was partly hidden behind the Milky Way itself. The hidden region has a simple astronomical name, the zone of avoidance. It sounds like a warning, but it began as a description of incomplete maps. When astronomers plotted the positions of distant galaxies across the sky, they found a broad empty band running along the plane of the Milky Way. Galaxies appeared everywhere else, yet within this band, their numbers fell sharply. The missing galaxies were not truly missing. They were concealed behind our own. From Earth, we look outward from inside the Milky Way's disk. In some directions, especially above and below that disk, the view opens into intergalactic space. In others, the line of sight passes through thousands of light years of stars, gas, and dust before reaching anything beyond the galaxy. The center of the Milky Way presents the most crowded view of all. There, countless stars overlap. Dark clouds block visible light. Bright nebulae, stellar remnants, and dense fields of foreground objects fill the same small regions of sky where distant galaxies would otherwise appear. A galaxy tens of millions of light years away may be large and luminous, yet from our position it can vanish behind a patch of dust much closer to home. This creates a peculiar problem. The Milky Way is the place from which astronomy is done, and at the same time, it is one of the main obstacles to seeing the larger universe around us. Early galaxy surveys depended heavily on photographic plates exposed to visible light. On those plates, the zone of avoidance looked sparse. Galaxies faded as the survey approached the galactic plane, then returned on the other side. The empty band divided the extragalactic sky and left major structures partly disconnected. A cluster might be visible north of the plane and another concentration south of it, while the bridge between them remained unseen. A filament could seem to end where it entered the Milky Way's glow. Motions suggested mass in the hidden region, but visible maps could not show enough of it, and the direction of the Great Attractor passed directly through this difficult part of the sky. The problem was not only that dust dimmed distant objects. Crowding mattered too. Even where some light passed through, the background was packed with foregrounds, stars. A faint galaxy could be mistaken for a small cluster of stars, blended into the luminous field, or lost inside uneven patches of emission. Astronomers needed other kinds of light. Dust does not block every wavelength equally. Visible light is scattered and absorbed strongly, but longer infrared wavelengths pass through much more easily. Radio waves can travel through even denser regions. X-rays reveal hot gas that may remain visible when ordinary starlight is heavily obscured. Each wavelength offered a different way to look through the Milky Way. Infrared surveys began filling in the stellar and galactic landscape behind the dust. Galaxies that were nearly invisible in optical images emerged as extended shapes. Their older stars, glowing strongly in infrared light, could be separated from some of the foreground clutter. The 2-micron all-sky survey, usually called 2MASS, mapped the entire sky in near-infrared wavelengths. It did not erase the zone of avoidance, because the galactic plane remained crowded and some dust clouds were still too thick, but it revealed structures that visible light maps had only hinted at. Radio astronomy opened another path. Neutral hydrogen atoms emit a characteristic radio signal with a wavelength of about 21 centimeters. Many spiral galaxies contain large reservoirs of this hydrogen. Radio telescopes can detect the signal through regions where dust makes visible observations nearly impossible. A hidden galaxy may not show its stars clearly, yet its hydrogen can announce its presence. By scanning the galactic plane at 21 centimeters, astronomers found galaxies behind the Milky Way and measured their redshifts at the same time. The signal provided both a detection and a way to estimate motion along the line of sight. These surveys began turning the blank band into a populated region. Not every galaxy could be found this way. Elliptical galaxies often contain little neutral hydrogen, and very distant signals can become faint. Strong radio emission from the Milky Way can also interfere. Still, the method uncovered many gas-rich galaxies and helped connect structures on opposite sides of the obscured sky. X-ray observations added a different layer. Large galaxy clusters contain enormous quantities of gas, heated to tens of millions of degrees. At those temperatures, the gas shines in X-rays. A cluster may be partly hidden in visible light, while its hot atmosphere remains detectable at higher energies. This became especially important near the traditional Great Attractor region. There, in the constellation Norma, astronomers identified a rich cluster of galaxies located behind the Milky Way's plane. It is often called the Norma cluster, and in astronomical catalogues, it is known as Abell 3627. The cluster lies roughly 200 million light-years away. It contains hundreds of galaxies bound together by gravity, immersed in a large reservoir of hot X-ray emitting gas. Much of its mass is not in the visible stars, or even in the hot gas, but in the dark matter inferred from the motions of galaxies and the behavior of the cluster as a whole. The Norma cluster is one of the most massive known structures in the nearby universe. For a time, it seemed to offer a satisfying answer. A massive cluster stood close to the direction indicated by peculiar velocities. It occupied the right region of space. It possessed enough matter to influence neighboring galaxies, but it could not explain everything. The flow extended across too wide an area. Some galaxies appeared to be responding to structures beyond Norma. The inferred motion of the local group could not be reduced to the gravitational influence of one cluster, even one as massive as this. The Great Attractor remained useful as a regional name, but the idea of a single central attractor began to fade. What emerged instead was a network. The Norma cluster belongs to a larger arrangement of galaxy groups, clusters, and filaments. These structures are part of the cosmic web, the immense pattern formed as gravity gathered matter around slightly denser regions in the early universe. The web is not uniform. Some filaments carry long chains of galaxies. Some intersections hold dense clusters. Between them lie sheets, walls, and broad underdenser spaces. Matter is not distributed like sand spread evenly across a floor. It is arranged more like a three-dimensional network of rivers and basins, although even that image is only an approximation. The Great Attractor region is one of those gravitational basins. Galaxies within a broad volume tend to move toward the denser structures inside it. Their paths are not straight lines aimed at one hidden point. They are shaped by the combined pull of nearby clusters, more distant concentrations, and the evolving geometry of the surrounding web. Mapping this required more than finding galaxies. Astronomers also needed to estimate how mass was distributed, including matter that emitted little or no light. Galaxy counts offered one guide because visible galaxies tend to trace underlying concentrations of matter. X-ray gas revealed deep cluster potentials. Gravitational effects supplied for further evidence of hidden mass. Peculiar velocities showed how the landscape was influencing actual motion. Different maps did not always agree perfectly. Each was built from incomplete measurements. Dust remained an obstacle. Distance estimates carried uncertainty. Some regions were sampled more densely than others. The conversion from visible galaxies to total mass depended on assumptions about how ordinary matter followed dark matter. Yet the broad pictures became clearer. The empty band was not empty. The Great Attractor was not a solitary object. The Milky Way was moving through a populated and uneven region shaped by many sources of gravity. There is something fitting about the way this understanding developed. The first evidence came from motion, from galaxies behaving as though something lay beyond the visible map. Only later did observations at other wavelengths begin to uncover the hidden structures themselves. The pull was measured before the landscape was seen, and even after the zone of avoidance began to open, the story did not end at the Norma cluster. Beyond it, farther into the same general region of sky, another concentration of galaxies was waiting on a much larger scale. Far beyond the Norma cluster, the same region of sky grows denser again. At a distance of roughly 650 million light-years, thousands of galaxies gather into one of the greatest concentrations of matter in the nearby universe. It is known as the Shapley supercluster, or more carefully, the Shapley concentration. Its distance places it more than 3 times farther away than the traditional Great Attractor region. The light reaching us tonight began its journey long before complex life spread across Earth's continents. It has crossed intergalactic space, while stars were born, aged, and disappeared, carrying an image of a structure that existed hundreds of millions of years in the past. What that light reveals is not one cluster. It reveals clusters beside clusters, groups between them, and long arrangements of galaxies extending through space. More than 8,000 galaxies have been associated with the broader concentration, and estimates of its total mass reach into the range of 10 quadrillion suns, depending on where astronomers draw its boundaries and how they account for dark matter. The Sun is one star among hundreds of billions in the Milky Way. The Milky Way is one galaxy among thousands in Shapley. Even that comparison does not fully convey the scale, because most of Shapley's mass is not contained in stars. It lies in dark matter surrounding galaxies and clusters, along with enormous reservoirs of hot gas spread between them. The densest core is centered near a cluster called Abell 3558. Around it are other rich clusters, including Abell 3556 and Abell 3562. Their galaxies are not sitting in finished, orderly arrangement. Observations indicate that parts of the core are interacting and merging, with clusters and smaller groups moving through one another. The spaces between the galaxies are filled with gas heated to millions of degrees. This gas shines in X-rays, allowing orbiting observatories to trace regions where ordinary visible images show only scattered points of light. X-ray maps make the concentration look almost fluid. Bright knots mark the deepest gravitational wells. fainter emission stretches between them. The pattern records collisions that unfold over hundreds of millions of years. As clusters approach, gas is compressed, and shock fronts move through the material between galaxies. The galaxies themselves usually pass one another without colliding. They are too widely separated for direct impacts to be common, but the gas surrounding them cannot pass through so easily. It is slowed, heated, and disturbed, preserving evidence of the encounter long after the first approach. Dark matter behaves differently again. It does not produce light, and it interacts only weakly with ordinary matter except through gravity. Astronomers reconstruct its distribution by studying the motion of galaxies, the temperature of cluster gas, and the subtle bending of light from more distant objects. In this way, Shapley becomes visible through several overlapping maps. One map is made from galaxies, another is made from hot gas, another is inferred from gravity. None is complete by itself. Together they reveal a region where matter has gathered much more densely than the cosmic average. The first hint of this concentration appeared long before modern digital surveys. In the 1930s, American astronomer Harlow Shapley studied photographic plates of the southern sky. On those plates, he noticed an unusual cloud of galaxies in the constellation Centaurus. The images were made from long exposures on glass, and every galaxy had to be identified against the grain and imperfections of the photograph. Shapley could not map the dark matter or measure the hot gas. He could not know the full three-dimensional arrangement of the objects, but he recognized that the concentration was real and unusually rich. Later surveys confirmed that the apparent cloud was part of a much larger structure, and the region eventually took his name. There is a generational thread running through measurements like these. One observer marks faint smudges on a photographic plate. Decades later, another records their spectra. A later survey measures thousands of redshifts at once. X-ray telescopes reveal gas between the galaxies, while gravitational lensing studies estimate the mass that cannot be seen directly. No single generation finishes the map. Each adds another layer to an object whose light was already crossing space before the first telescope existed. When astronomers began connecting Shapley with the Great Attractor problem, the geometry seemed persuasive. The concentration lies in approximately the same broad direction as the local group's motion against the cosmic microwave background. It is massive, and it sits beyond the Hydra Centaurus and Norma regions, where earlier maps appeared to stop. This raised a natural possibility. Perhaps the Great Attractor was not the final destination of the flow. Perhaps the nearer structures were themselves being drawn toward Shapley. Gravity weakens with distance, but distance is only one part of the calculation. A remote concentration can still exert a measurable influence if it contains enough mass and extends across a large enough region. Shapley is distant, yet its collection of clusters is so substantial that it cannot be ignored when reconstructing the motion of the local universe. The effect is not like a rope tied between 2 points. Every concentration of matter contributes a gravitational acceleration. Nearby galaxies contribute. The Virgo cluster contributes. The Norma region contributes. Shapley contributes. Countless smaller groups add weaker terms, while underdense regions alter the balance by providing less pull from other directions. The final movement is the sum of all of them. This is why estimates of Shapley's contribution have varied. Different surveys cover different volumes. Some rely on galaxies selected in infrared light. Others use X-ray clusters, supernova distances, spiral galaxy rotation, or the internal motions of elliptical galaxies. Each method samples the universe in its own way and carries its own uncertainties. The boundary of Shapley is also difficult to define. A galaxy cluster can often be recognized as a gravitationally bound system. A supercluster is less tidy. It may include dense cores that are bound, wider filaments that are still evolving, and outer regions that will continue separating as cosmic expansion accelerates. Calling all of it one object is useful for mapping, but nature does not always provide a sharp outer edge. A survey covering the Shapley region found that its galaxies extend through sheets and filaments across tens of millions of light years. Some of these structures connect major clusters, others fill spaces once assumed to be relatively empty. The concentration is not a compact ball of matter. It is a complicated section of the cosmic web. This changes how the word attractor should be understood. An attractor on a map of cosmic motion is not necessarily a permanent destination. It may be the point toward which reconstructed flow lines converge at a particular scale and under a particular method of smoothing the data. At small scales, nearby structures dominate. When the map is smoothed across greater distances, smaller features blend together and larger concentrations become more important. The apparent center of motion can shift from the Virgo region toward Hydrus Centaurus, and then toward Shapley. The destination changes because the scale of the question changes. It is similar to studying the slope of a landscape from different heights. Standing close to the ground, a small hollow may determine where rainwater moves. Seen from above, that hollow belongs to a wider valley. From farther away, the valley itself becomes one branch of a much larger drainage system. No view is false. Each reveals a different level of the same terrain. Recent reconstructions of the nearby universe reinforce this layered picture. They indicate that no single cluster, supercluster, or classical Great Attractor can account for the full motion of the local group. Even when astronomers include matter across hundreds of millions of light years, part of the observed velocity remains connected to structures beyond the chosen survey volume and to the complex way local motions combine. Shapley remains one of the major influences, but it is not a solitary answer. This distinction matters because the local group is not traveling along a fixed road to one final point. Its motion is being continually shaped by the distribution of matter around it. Nearby structures create stronger, immediate accelerations. Distant concentrations add broader components. Voids reduce the pull from directions where matter is scarce. The resulting path is curved through three-dimensional space. It changes as galaxies and clusters move, as matter continues gathering, and as the expansion of the universe gradually alters which regions can remain connected. Even the word pulling can be misleading if it suggests an active force reaching across empty space from a single source. In general relativity, matter changes the geometry through which other matter moves. The local group follows that uneven geometry, responding to the combined structure of its surroundings. From where we rest on Earth, none of this motion can be felt. The solar system moves with the Milky Way. The Milky Way moves with nearby galaxies. The larger current carries the entire local environment together, leaving no nearby stationary platform against which the motion could be noticed. Only the oldest light provides the reference. Only large surveys reveal the terrain, and only by combining many imperfect measurements does the hidden movement begin to take form. The Shapley concentration widened the Great Attractor story beyond the nearer clusters. It showed that the gravitational field shaping our motion extends much farther than early maps could easily reach. Yet Shapley does not close the map. Other structures lie beyond and beside it. Some are partly concealed by the Milky Way. Some occupy directions where fewer galaxies create an influence through absence rather than abundance. The current carrying our galaxy is not flowing toward one isolated island. It is moving through an entire cosmic watershed. A watershed is usually imagined beneath an open sky. Rain, some water runs toward one river, while water on the opposite slope begins a different journey. The boundary may be narrow enough to cross in a few steps, even though the rivers it separates eventually reach distant seas. In 2014, astronomers borrowed this idea for the motion of galaxies. They were not tracing water, and there were no solid ridges between one region of space and another. They were tracing a reconstructed velocity field, built from measured galaxy distances and redshifts. Wherever the flow lines converged toward the same gravitational basin, the galaxies were treated as belonging to one large dynamical region. That region was named Laniakea. The word comes from Hawaiian and is commonly translated as immense heaven. The name acknowledged the Pacific navigation traditions that used knowledge of the sky to cross large distances, and it was chosen for a structure so broad that the Milky Way occupies only a small place near one of its outer reaches. The original reconstruction described Laniakea as extending roughly 500 million light-years across. Its inferred mass was on the order of 100 quadrillion suns. Within its boundary were the local group, the Virgo cluster, the Hydra Centaurus region, and the classical Great Attractor. The Milky Way was not near the center. It sat along a minor branch of the flow, far from the deepest part of the basin. The nearby galaxies around us appeared to move first toward the Virgo region, then into a larger current leading toward the Great Attractor area near the Norma cluster. On the map, this looked like a network of fine luminous threads. Each thread represented the reconstructed path that matter would follow under the surrounding gravitational field after the smooth expansion of the universe had been accounted for. Nearby streams joined larger ones. Those larger streams bent toward a common region. Along the outer boundary, the direction changed. Galaxies just beyond that surface belonged to neighboring basins, with their flow lines turning elsewhere. This was a new way to define a supercluster. Earlier superclusters were often identified mainly from the positions of galaxies. Astronomers found dense groupings, walls, and filaments, then gave names to the large structures they seemed to form. But density maps can leave uncertain boundaries. A filament may continue into another concentration. A broad chain of clusters may look connected even when its parts are not moving toward the same destination. A velocity watershed offered a different rule. Instead of asking only where galaxies are, it asks where they are going. The distinction is important because the universe is expanding. On the largest scales, distant regions are being carried apart. A supercluster does not have to be a single, fully bound object, like a galaxy cluster. Much of it may never collapse into one final structure. The name can describe a shared pattern of motion now, even when cosmic expansion will eventually separate some of its outer regions. Laniakea was therefore not a giant island floating intact through space. It was a dynamical basin reconstructed from the present flow of galaxies. To build that reconstruction, astronomers began with peculiar velocities. For each galaxy or group with a measured distance, they estimated the motion left after subtracting the expected cosmic expansion. These observations were uneven and uncertain, so the raw data could not simply be connected point by point. A statistical method was needed to infer the most likely velocity and density fields between the measurements. The reconstruction assumed the broad framework of modern cosmology, including a universe in which structure grows from early density differences under gravity. It used the observed motions as constraints, then estimated the underlying field that could have produced them. Where data were sparse, uncertainty increased. Where many reliable measurements agreed, the flow became clearer. This is why the boundary of a cosmic watershed is not a visible wall. It is a surface in a model, supported by observations, but dependent on their depth, quality, and coverage. Improve the catalogue, and the inferred surface may move. Extend the survey farther, and a basin that once seemed separate may become part of a larger system. The first Laniakea map was based on the Cosmic Flows 2 catalogue, which contained distances for thousands of galaxies. Later compilations expanded that foundation. Cosmic Flows 4 brought together distance estimates for more than 50,000 galaxies, organized into roughly 38,000 groups. The larger catalogue reaches farther and samples more of the sky. It also reveals why cosmic addresses are not permanent in the way postal addresses are. With deeper data, researchers have reconstructed several neighboring basins, including Shapley, Perseus Pisces, Hercules, and others. Some analyses continue to recover Laniakea as a meaningful dynamical region. More recent work, however, finds a modest statistical preference for placing the area traditionally called Laniakea inside the much larger basin associated with Shapley. This does not mean the earlier map was careless. It means the map was made at a particular depth and resolution. A shoreline drawn from a low-flying aircraft may show individual coves. Seen from orbit, those coves belong to one larger coast. In the same way, a local convergence around the Great Attractor can remain physically useful, even if a deeper reconstruction shows that its broader flow ultimately joins the Shapley Basin. The name Laniakea still describes our local cosmic environment in many discussions. It gives a recognizable form to the network containing the Milky Way and the nearby structures that first shape our motion, but its exact status depends on how a supercluster is defined and on which velocity data are used. There is no contradiction in saying that we live within Laniakea, and that Laniakea may be nested inside a larger Shapley-centered basin. Cosmic structure is hierarchical. Earth belongs to the solar system. The solar system belongs to the Milky Way. The Milky Way belongs to the local group. The local group lies within a local sheet of galaxies and participates in flows connected with Virgo, the Great Attractor region, and Shapley. Each level answers a different question. The local group describes galaxies bound closely enough to share a common future. Laniakea describes a much broader pattern of velocity convergence. The Shapley Basin describes a deeper gravitational organizations visible when the map extends farther. The boundaries need not match because the definitions do not ask the same thing. This layered view also changes the meaning of our 600 km/s motion. The local group is not simply falling toward a dot labeled Great Attractor. Part of its velocity was acquired through the accumulated gravitational influence of structures across a wide range of distances. Some of that motion reflects nearby asymmetry. The Virgo cluster lies off in one direction, while the distribution of galaxies around the local group is not balanced evenly. Farther away, Hydra, Centaurus, and Norma deepen the field. Beyond them, Shapley contributes across a much greater volume. The velocity we measure now is the result of these influences acting over cosmic time. Gravity has been shaping the path of our matter since long before the Milky Way took its present form. The atoms beneath you were once part of gas that moved inside the growing cosmic web. Before the Sun existed, the material of the future solar system already shared the broader motion of the galaxy. The present velocity is not a new journey that began when astronomers noticed it. It is one moment in a continuous fall through an evolving landscape, and that fall does not lead to a collision with the Great Attractor. The distances are too large, the structure too distributed, and the universe too dynamic for such a simple ending. The Milky Way has its own nearer future, including its gravitational interaction with Andromeda and the evolution of the local group. At larger scales, accelerating expansion limits which regions can ever gather together. Some parts of a velocity basin may approach one another, other parts will remain separated, their shared present motion gradually giving way to the expansion between them. A basin of attraction is therefore best understood as a map of tendency, not a promise of arrival. It shows how the universe is moving now, based on the matter we can observe and infer. It reveals the channels through which galaxies stream and the surfaces where one broad flow gives way to another. But it does not freeze those channels forever. The cosmic web continues to evolve, Clusters grow by drawing in galaxies and groups. Filaments feed dense regions. Voids expand as matter leaves them behind. Dark energy increasingly influences the behavior of the largest scales, preventing many distant structures from becoming one bound object. Against this changing background, the Milky Way's location becomes both more precise and less final. We can place it inside a local group along a local sheet, near the edge of a reconstructed Laniakea watershed and within the wider influence of Shapley. Each address is useful. None is the last line that can be written. For a listener beneath the night sky, this motion remains completely shared. The bed, the building, the ground, the planet, and the stars of the Milky Way all take part in it together. Nothing nearby is left behind to mark the passage. Only when our measurements reach beyond the galaxy does the current become visible. Laniakea gave that current a shape. It transformed the Great Attractor from an isolated mystery into part of a branching system of flows. It showed that the question was not merely what is pulling us, but how the surrounding universe divides into regions of common motion. And once astronomers began thinking in watersheds, another influence became impossible to ignore. A galaxy can be guided not only by the matter ahead of it, but also by the emptiness behind. Emptiness does not pull in the ordinary sense. A cosmic void contains less matter than the universe around it, so there is no hidden force pushing galaxies outward from its center. Gravity remains attractive everywhere. What changes is the balance. A galaxy side, an underdense region feels less gravitational attraction from the direction of the void, and more from the denser walls, filaments, and clusters on the opposite side. The result can look like repulsion. Imagine two small boats drifting between unequal currents. One side draws more strongly than the other. The boats move toward the stronger flow, and from the weaker side, they appear to be pushed away. Nothing inside the weaker current is actively repelling them. The imbalance alone shapes their motion. Cosmic voids influence galaxies in a similar way. They begin with small differences in density left from the early universe. Regions containing slightly more matter attract additional material and become denser. Regions containing slightly less matter lose material to their surroundings. Over billions of years, the difference grows. Matter gathers into sheets and filaments while the underdense spaces between them become larger and emptier. A void is therefore not an untouched hole in the universe. It is an evolving region from which matter has gradually migrated. Some galaxies remain inside. They are often smaller and more widely separated than galaxies in crowded environments. Thin strands of matter may cross the interior, and dark matter is still present, though at a lower density than the cosmic average. Gas also remains spread so thinly that much of it is difficult to observe. The word empty is useful only by comparison. A room containing one person may feel empty beside a crowded station. A cosmic void is similar. It is not nothing. It is a region where the universe has placed far less matter than it has placed elsewhere. As the matter around a void gathers into its edges, the void expands relative to the surrounding cosmic pattern. Galaxies near its boundary tend to move outward into walls and filaments. When astronomers reconstruct those motions, the flow lines appear to diverge from the underdense center. This divergence creates what can be called a repeller. In 2017, researchers using galaxy distances from cosmic flows reconstructed the three-dimensional velocity field around the local group. Their model identified a large underdense region in nearly the opposite direction from the motion measured in the cosmic microwave background. They named it the dipole repeller. In the reconstruction, the broad local flow was shaped by both this underdensity and the distant concentration of matter around Shapley. The word dipole refers to the paired geometry. In one broad direction lies a major concentration of matter. In the opposing direction lies a large deficit. The local group moves between them. drawn more strongly toward the populated side, while receiving less gravitational resistance from the underdense side. The pattern resembles a slope formed in two ways at once. One side of the landscape rises because matter has accumulated there. The other falls because matter is missing. A ball placed between them rolls in a direction determined by both surfaces, not by the high ground alone. Shapley helps define one side of that cosmic slope. The dipole repeller helps define the other. This does not mean the two regions are perfect opposites, or that they alone explain every detail of our motion. The real universe contains many structures at many distances, but the paired arrangement provides a useful description of the largest component revealed by the reconstructed velocity field. It also corrects a long-standing habit in astronomy. Bright objects are easier to notice than empty regions. Galaxy clusters announce themselves through concentrated starlight, hot X-ray gas, radio sources, and gravitational lensing. A void offers far less to observe. Its influence may be measured most clearly through the movement of matter around it, rather than through anything shining at its center. For many years, explanations of the local group's motion therefore focused on attractors. The Great Attractor seemed to lie ahead. Shapley added a larger concentration beyond it. Both were visible, at least in portions of the sky where the Milky Way did not interfere. The dipole repeller required a different kind of attention. Its strongest evidence came from motion pointing away from a region where there were comparatively few luminous objects to count. The absence itself became part of the map. This idea is easier to understand through a nearer example. The Milky Way lies in a flattened arrangement of galaxies called the local sheet. Nearby systems, including Andromeda and many smaller galaxies, occupy this relatively narrow layer. Beside the sheet lies the local void, an underdense region beginning close to our galactic neighborhood. Measurements of nearby galaxy distances and velocities indicate that the local sheet has a substantial motion away from the local void. One analysis separated this movement into a component of about 260 kilometers per second. The same work found that the void must be large and deeply underdense to account for such a motion within standard gravitational structure formation. The local void and the dipole repeller are not the same feature. The local void is much closer and influences motion on a smaller scale. The dipole repeller was inferred farther away from a large-scale reconstruction, but the nearby void offers a more immediate example of the same underlying principle. Matter does not need to be pushed by an unknown force. An uneven gravitational field is enough. The local sheet sits near the edge of the local void rather than near its center. As matter has moved out of the underdense region and gathered elsewhere, the galaxies of the sheet have joined that outward flow. Other nearby structures contribute additional motion toward Virgo and toward more distant concentrations. These components do not line up neatly along one axis. They approach from different directions and combine like several currents meeting beneath the surface of the sea. One current may be associated with the nearest void. Another reflects the Virgo region. A larger component follows the structure extending towards Centaurus, Norma, and beyond. The motion of the local group is their vector sum. That phrase sounds abstract, but the idea is simple. Direction matters as much as speed. Two influences pulling at right angles do not simply add into a faster movement along either original path. They create a new direction between them. The local group's motion through the cosmic microwave background is built from many such contributions. Some arise within a few tens of millions of light years. Others come from much farther away. Some reflect dense concentrations. Others reflect the absence of comparable matter in opposing directions. By reconstructing these components, astronomers can begin to separate the local from the distant. They can ask how much of our movement is connected to Virgo, how much to the local void, How much to the Great Attractor region, and how much remains after those nearer effects are removed? The answers depend on the survey and the method. Peculiar velocities are difficult to measure. Distance errors grow with depth. The sky is not sampled evenly. Statistical filters must fill spaces between observations, and those filters work within assumptions about how structure grows. The dipole repeller is therefore best understood as a reconstructed feature supported by the observed velocity field, not as an object photographed directly. Later constrained reconstructions have continued to recover the major nearby clusters, superclusters, and void-like regions, including a robust underdensity associated with the dipole repeller. These methods use many possible realizations of the local universe to identify which features persist despite observational uncertainty. A feature that survives across many reconstructions becomes harder to dismiss as an accident of incomplete data. Yet its exact boundaries remain uncertain. Voids rarely have clean spherical edges. They can overlap, join, and contain smaller structures within them. Their shapes depend on how density is measured and on the scale used to smooth the map. A narrow underdense channel at one resolution may merge into a broad basin at another. The same caution applies to the word center. A reconstructed repeller marks the region from which flow lines diverge most strongly in a model. It does not imply a physical center where a new kind of energy resides. There is no evidence that the dipole repeller violates gravity or that it sends matter outward through a repulsive substance. It is ordinary gravity acting across an uneven universe. That ordinary explanation is more expansive than the dramatic one. It means emptiness participates in cosmic architecture without needing to become a thing. A missing concentration changes the balance around it. A low-density region helps guide galaxies because the competing pools are unequal. The shape of the universe is written not only by where matter gathers, but by where it does not. Voids also affect the future of the cosmic web. As dense regions continue drawing in material, void interiors become more rarefied. Their boundaries sharpen into walls and filaments. Smaller voids may merge into larger ones, while some underdense regions embedded within crowded environments can be compressed or erased. Across the largest scales, the volume occupied by voids grows. Galaxies remain concentrated along the web, tracing only a small portion of the available space. The universe becomes a network in which luminous matter outlines the borders of immense, low-density cells. From inside the Milky Way, those cells are difficult to perceive. The night sky presents stars in every direction. The galaxy surrounds us with light. But beyond the stellar foreground, most cosmic volume is not occupied by clusters or bright filaments. It belongs to regions where matter is sparse and distances between galaxies become immense. The Great Attractor story began with a search for hidden mass. It led toward Norma, then farther toward Shapley. But the full motion of the local group cannot be understood by looking only ahead. The opposing sky matters too. The route is shaped by the concentration in one direction and the deficit in another. Our galaxy is not simply falling towards something. It is moving away from emptiness at the same time. And when both sides of the landscape are included, the current begins to reveal its deeper geometry. The deeper geometry cannot be photographed in a single exposure. A telescope can record galaxies, glowing gas, and the bending of distant light. But a gravitational flow is not an object with an edge. It must be reconstructed from evidence scattered across the sky, gathered at different distances and measured with different kinds of uncertainty. The result is closer to a weather map than a portrait. A weather map does not show the wind itself. It combines pressure, temperature, moisture, and movement into a model of how the atmosphere is behaving. In the same way, cosmic flow maps combine galaxy positions, redshifts, independent distance estimates, and assumptions about gravity to infer how matter is moving through the nearby universe. The measurements begin as points. For one galaxy, astronomers estimate a distance and compare it with the motion indicated by its redshift. The difference gives only one component of peculiar velocity, the part directed toward or away from Earth. The sideways motion is usually far too small to measure at such distances. This means every galaxy provides an incomplete clue. We know how quickly it moves along our line of sight, but not its full three-dimensional path. Even that radial measurement may carry a large uncertainty because the inferred distance is never exact. Thousands of incomplete clues must therefore be joined. Cosmic Flows 4 was assembled for this purpose. It contains distance estimates for more than 55,000 galaxies, grouped into roughly 38,000 systems so that the random motions of individual galaxies within clusters do not overwhelm the larger flow. The catalogue combines several distance methods, each calibrated against overlapping measurements. The grouping matters. Inside a galaxy cluster, members may orbit their shared center at hundreds or even more than 1,000 kilometers per second. Those internal movements reveal the cluster's mass, but they can hide the slower motion of the entire cluster through the cosmic web. By treating related galaxies as a group, astronomers reduce some of that local noise. What remains is still uneven. Some parts of the sky contain many reliable distances. Others contain fewer. The northern and southern hemispheres have been surveyed by different instruments with different sensitivities. The plane of the Milky Way continues to obscure galaxies, even though infrared and radio observations have narrowed the hidden band. Distance uncertainty also grows more troublesome as the map reaches farther outward. A small percentage error at a nearby dest may represent only a few million light years. The same percentage applied much farther away can shift a galaxy across a substantial portion of a supercluster. Since peculiar velocity is found by subtracting two large quantities, an error in distance can create an apparent motion much larger than the true one. The reconstruction must account for this. One widely used method is called Wiener filtering. The name does not refer to anything physical in space. It is a statistical technique designed to recover an underlying signal from noisy and incomplete data. It weighs the observations against an expected pattern of cosmic structure, preserving features supported by measurements while allowing uncertain regions to relax toward the average behavior predicted by the model. Where data are dense, the reconstructed map follows them closely. Where observations are sparse, the map becomes smoother and less certain. Astronomers then create constrained realizations, many possible versions of the nearby universe that remain compatible with the measurements. One realization may place a filament slightly farther north. Another may alter the shape of a void or shift the center of a basin. Features that appear repeatedly across many versions are considered more secure than those present in only a few. This allows uncertainty to become part of the map rather than something hidden behind it. Instead of asking for one perfect reconstruction, researchers ask which structures survive when the uncertain measurements are allowed to vary. Virgo survives. The Shapley concentration survives. The large underdense regions survive. The broader flow through the Hydra Centaurus direction survives, though the exact convergence point changes with the depth of the data and the scale at which the velocity field is smoothed. Smoothing is one of the most important choices in this work. A detailed map preserves small structures. It may show galaxies streaming toward the Virgo cluster, toward nearby groups, or away from the local void. A more heavily smoothed map blends these features together and reveals wider movement toward Hydra, Centaurus, or Shapley. The mathematics has not changed the universe. It has changed the scale of attention. Consider a landscape covered with stones, channels, hills, and valleys. If every small feature remains visible, water appears to follow thousands of separate paths. Smooth the landscape in imagination, and the smaller channels disappear. Several streams become one river, while several local depressions become part of one broad basin. The cosmic velocity field behaves in the same layered way. At relatively fine resolution, our local flow can appear to converge toward Virgo. At an intermediate scale, the Hydra Centaurus region becomes prominent. At still larger scales, the convergence shifts toward Shapley. Recent digital reconstructions of the nearby universe have emphasized that these are not competing answers. They are scale-dependent descriptions of a velocity field produced by many structures. A 2026 simulation study found that no single proposed attractor dominates the local group's velocity, and that the apparent convergence point changes from Virgo to Hydra Centaurus, and then to Shapley as the smoothing scale increases. Arashiv. This helps resolve an old ambiguity in the name Great Attractor. The phrase has been used for at least 3 different questions. What mass produced the local group's observed velocity? Where do present-day reconstructed flow lines converge? And where will the local group ultimately travel? Those questions sound similar, but they do not require the same answer. The velocity we measure now was accumulated through gravitational influence over a long span of cosmic history. Matter both near and far contributed to it. A present-day streamline, however, is drawn from the velocity field at one moment. It shows the local direction of motion under a smoothed reconstruction, not a complete record of every influence that created the velocity. The future path is different again. Galaxies continue to move, clusters merge. The balance between nearby structures changes. The expansion of the universe increasingly separates regions that are not gravitationally bound. Following a streamline drawn today does not guarantee that a galaxy will reach the point where that line presently ends. A current map is not a railway track. It is a description of movement now. This distinction becomes clearer in computer simulations. Researchers begin with a cosmological model and a set of initial conditions consistent with observations. Dark matter, gas galaxies, and expanding space are then allowed to evolve under gravity. When the starting conditions are constrained by real measurements, the simulation can develop recognizable versions of nearby structures. Virgo appears in approximately the correct direction. The local void opens nearby. Filaments form around Hydra and Centaurus. A distant concentration emerges where Shapley is observed. These simulations are sometimes called digital twins of the local universe. The phrase does not mean that every individual galaxy is copied exactly. Rather, the broad density field and its major structures resemble the region around us closely enough to explore its dynamics. Many twins are created because the observations allow more than one possible history. In one version, the local group passes slightly closer to a filament. In another, a nearby cluster is more massive. Across the collection, researchers can identify which aspects of our motion remain stable and which depend on uncertain details. The most recent analyses suggest that matter within a wide region around us explains much, but not all, of the local group's motion relative to the microwave background. One simulation study estimated that mass within roughly 200 million light-years, after adjustment for the chosen cosmological distance scale, accounted for about 72% of the measured speed, with a notable difference between the predicted and observed directions. The result reinforces the idea that more distant structures and smaller scale effects still contribute. This is not evidence that gravity has failed. It is evidence that the accounting remains incomplete. The farther a gravitational reconstruction extends, the harder the observations become. Distances grow less precise. Selection effects become stronger. Some regions receive far more coverage than others. Matter outside the mapped volume can still influence everything inside it. creating what astronomers call a tidal field. The word tidal is used because distant matter can produce different accelerations across a region. The Moon creates tides on Earth because its gravity is slightly stronger on the near side than on the far side. In the same broad sense, structures beyond a cosmic survey can distort the velocity field within it. Their individual details may not appear on the map, yet their combined influence can remain. A reconstruction with a boundary is therefore never completely isolated. The universe continues beyond the edge of the catalogue. This is one reason measurements of bulk flow receive so much attention. Bulk flow is the average peculiar motion of galaxies within a chosen volume. As the volume grows, local motions should partly cancel, leaving a smaller residual movement if the sampled region becomes representative of the universe as a whole. The approach toward that calm statistical behavior is called dynamical homogeneity, but determining the scale at which it occurs is difficult. Different surveys and methods have produced somewhat different results. Cosmic flows, 4 reconstructions have found a large-scale flow broadly oriented towards Shapley, with some analyses describing an amplitude higher than the average expected in standard cosmological simulations, though not so unusual that the standard model is decisively contradicted. This is where careful language matters. An unusual measurement is not automatically a crisis. A 2 or 3 sigma difference can arise in a standard universe, especially when observations contain complicated selection effects, and the reconstructed volume is not sampled uniformly. It may point toward missing data, underestimated uncertainty, or a real but uncommon arrangement of nearby structures. Further measurements decide which possibility becomes more likely. New surveys are improving the map from several directions at once. Large redshift programs record the positions and spectra of millions of galaxies. Radio telescopes detect hydrogen behind the Milky Way. Measurements of supernovae and galaxy rotation refine distances. Statistical methods are becoming better at correcting biases that can imitate large flows. Yet more data do not always make the picture simpler. They may reveal that a named structure has no clean boundary. They may divide one apparent basin into several, or combine several into one. They may show that a familiar attractor was only a useful marker within a more complicated field. This is not a failure of naming. Names provide temporary handles for regions whose full geometry cannot be held in ordinary thought. The Great Attractor, Laniakea, and the Shapley Basin each capture a real pattern at a particular stage of observation. Their meanings become more precise by becoming less absolute. The map now suggests a universe without one final arrow. Our galaxy's motion is assembled from nearby falls, distant tides, expanding voids, and the inherited momentum of matter moving through the web. Every reconstructed line is part of a field that continues beyond the survey and backward into deep time. What seemed at first like a hidden object has become a problem of relationships. Gravity is distributed, motion is layered, and the direction we call forward depends on how much of the universe we are able to see. The map is still being drawn. Some of its missing pieces are hidden behind the Milky Way. Others lie so far away that the small motions of galaxies become difficult to separate from the expansion of space. Many are hidden not by distance alone, but by the limits of the measurements themselves. The next improvements will come from seeing more galaxies and measuring them in more than one way. Large surveys can record redshifts for millions of objects, building a denser picture of where matter has gathered. Infrared observations can reach through portions of the galactic plane. Radio surveys can trace neutral hydrogen in galaxies whose starlight is difficult to distinguish from the foreground. X-ray telescopes can identify massive clusters through the hot gas held inside their gravitational wells, but positions and redshifts reveal only part of the landscape. To understand motion, astronomers still need reliable distances. That requirement has shaped the Great Attractor story from the beginning. A galaxy's redshift contains both the expansion of the universe and its own movement through local space. Without an independent distance, the two remain tangled together. Future catalogues will improve the distance scale by combining many indicators. Pulsating stars will continue to anchor nearby measurements. The brightest stars in old stellar populations will extend the ladder outward. Rotating spiral galaxies and the internal motions of elliptical galaxies will provide estimates across larger volumes. Supernovae will offer temporary but powerful distance markers when they appear. Other methods may eventually become more important. When two neutron stars merge, they disturb space-time and produce gravitational waves. The shape of that signal can reveal a distance without relying on the usual ladder of stellar brightness. If astronomers can also identify the host galaxy, the event becomes what is called a standard siren. One such event does not remap the local universe. Many events, spread across the sky, could provide an independent set of distances. They may help test the calibration of existing methods and strengthen measurements of peculiar velocity across regions where current estimates remain uncertain. The changing sky may also offer new clues. Over long periods, galaxies shift position by amounts too small for present instruments to detect easily. Their sideways movements are far harder to measure than motion along the line of sight. Yet, improvements in astrometry could one day reveal parts of this transverse flow directly. A complete three-dimensional velocity would remove some of the guesswork from cosmic maps. For now, most reconstructions must infer sideways motion from the surrounding pattern. They use gravity and the known distribution of matter to estimate how the missing components should behave. Direct measurements would test those inferences and show whether the flow bends as expected. The cosmic microwave background will remain the broadest reference. Its dipole tells us how the solar system moves relative to the ancient radiation field. But future measurements may refine other subtle patterns connected to the motion of matter between us and that background. Clusters of galaxies can slightly alter microwave photons as they pass through hot gas. Their motion adds another small effect, shifting the radiation according to whether the cluster approaches or recedes. Measuring this signal across many clusters can provide an additional view of large-scale velocity. Each technique sees the current differently. Galaxy distances follow individual systems. Microwave measurements sample clusters and ionized gas. Gravitational lensing traces mass, whether or not it shines. X-rays reveal the deepest wells filled with heated material. Simulations connect all of these observations to the growth of structure over time. The most reliable picture will come from their agreement. It may show that the familiar names remain useful. Virgo may continue to describe the nearest major influence. The Great Attractor may remain a practical label for the convergence around Hydra, Centaurus, and Norma. Shapley may remain the strongest distant concentration in the surrounding volume, or the boundaries may change again. A deeper survey might reveal that one named basin belongs to a broader flow. A new concentration could appear behind the Milky Way. Better distances could weaken a feature or strengthen an underdensity that had been only faintly reconstructed. This uncertainty does not make the present map empty of meaning. It tells us what kind of map it is. A cosmic flow map is not a finished chart of fixed continents. It is a reconstruction of movement across a universe whose structures continue to evolve. Its lines depend on measurements, scale, and the moment at which the flow is described. There may never be one permanent answer to the question of what is pulling the Milky Way. At one scale, the answer is the nearby distribution of galaxies. At another, it is the Great Attractor region. Farther outward, Shapley becomes important. Include the opposite sky, and the voids become part of the explanation. Look back through cosmic time, and the answer becomes the entire history of uneven matter gathering under gravity. Every answer is contained inside a wider one. This layered structure is not unique to astronomy. Long before galaxies were mapped, people learned direction from skies that appeared stable. A navigator did not need to know the motion of the local group to use a star near the horizon. The star's position within the night was enough for the journey at hand. Modern astronomy works with a different horizon, but the habit is related. A reference is chosen. A motion is measured against it. The scale of the journey determines which map is useful. For travel across an ocean, the rising point of a star may be enough. For travel between planets, the positions of the sun and worlds must be known with far greater precision. For the motion of galaxies, even the Milky Way is too close to serve as a stationary background. The reference must be carried outward to the oldest light. Against that distant field, our entire local environment is moving. You do not feel this motion because feeling requires a local difference. A sudden turn can be felt. A vibration can be felt. A change in speed can press against the body. But shared motion leaves little trace when everything nearby moves together. The Earth does not trail behind the Sun. The Sun does not trail behind the galaxy. Your surroundings remain arranged around you while the whole system follows its path through the cosmic web. At this moment, the Milky Way is moving relative to the microwave background. The local group is responding to nearby clusters, larger concentrations, and the absence of matter inside neighboring voids. The solar system is circling the galactic center while the galaxy itself participates in that broader flow. These motions pass through one another without conflict. There is no single speed that belongs to you in an absolute sense. Relative to the room, you may be at rest. Relative to Earth's axis, you are turning. Relative to the Sun, you are orbiting. Relative to the center of the Milky Way, the Sun is sweeping around the galaxy. Relative to the microwave background, the local group is crossing space at hundreds of kilometers each second. Rest and motion depend on the chosen frame. The Great Attractor became compelling because it seemed to offer a final frame, a hidden destination that could explain the arrow. What astronomers found instead was a hierarchy of frames, each revealing another part of the movement. The mystery did not disappear. It changed form. The question is no longer only where the mass is located. It is how gravity from many regions combines, how voids reshape the balance, how far the relevant structures extend, and how accurately the present flow can be reconstructed from light that left distant galaxies millions of years ago. Even the map of today is assembled from the past. A galaxy 200 million light years away is seen as it was 200 million years ago. Its position, brightness, and spectrum arrive together, but they do not show its present state. The gravitational field around us must be inferred from a universe observed at many different times, layered by distance across the sky. Astronomers correct for this as carefully as possible. They use models of how structure grows. They compare observations with simulations. They test whether the reconstructed matter can produce the measured velocities. The work becomes an act of translating light from different ages into one coherent picture of motion. That picture will continue to improve, yet its deepest lesson may already be clear. The Milky Way is not being carried toward one isolated object. It is participating in the slow organization of matter across the cosmic web. Its motion belongs to a wider pattern, formed from abundance and absence, from clusters and voids, from nearby gravity and distant structure. The arrow points outward only because the rest of the map surrounds it. The motion does not lead to a single destination. It continues through a universe that is changing on every scale. Nearby galaxies remain bound by their shared gravity. Clusters gather more slowly. Filaments feed dense regions. Voids widen as matter drains toward their edges. Beyond them, The expansion of space keeps increasing the distance between structures that are too far apart to remain connected. The local group has a nearer future than the Great Attractor. The Milky Way and Andromeda are moving toward one another, not because of Shapley or Norma, but because they are the two dominant galaxies in the same small gravitational system. Their encounter will unfold over billions of years, long before any motion toward a distant supercluster could become an arrival. The structure of our own galactic neighborhood will have changed. The stars inside the two galaxies are unlikely to collide directly. Their separations are too large, but their orbits will be rearranged as the galaxies pass through one another, separate and return. Gas clouds may compress, new stars may form, tidal streams may stretch into space. Over time, the two systems are expected to settle into one larger galaxy, surrounded by many of the smaller companions that already belong to the local group. This future remains local. The local group is gravitationally bound strongly enough to resist the expansion of the universe within its own borders. The space between its members does not simply grow as it does between distant, unbound galaxies. Gravity has already drawn these galaxies into one shared system. The Virgo cluster lies much farther away. Although our local galaxies have a velocity component in its direction, that does not mean the local group will eventually fall into Virgo. The accelerating expansion of the universe changes what can remain connected across such distances. Matter that is not already bound into the same structure may continue to separate even when present-day velocity maps show a flow toward a common region. The same caution applies to the Great Attractor and to Shapley. They help explain the motion we measure now. They shape the surrounding velocity field, but they are not guaranteed endpoints waiting at the end of a cosmic road. A flow line can be drawn from present data, yet the future landscape will not remain fixed while a galaxy travels through it. Every cluster moves, every filament evolves, the balance of attraction changes. Expansion stretches the distances between large structures, and dark energy becomes increasingly important on the widest scales. For this reason, the Great Attractor is best understood as part of a history of motion rather than a place where the Milky Way must one day arrive. The matter in our galaxy has been responding to uneven gravity since the early universe. Long before the Sun formed, the region that would become the local group was already embedded in a web of growing density. Nearby overdensities gained matter, underdenser regions lost it. Small motions accumulated over billions of years until they became the large peculiar velocity measured against the cosmic microwave background today. The present speed is a kind of inheritance. It carries the influence of structures that formed, merged, and shifted across deep time. Some of those structures remain visible. Others have changed since the light we now receive left them. The motion beneath the night sky is therefore not a response to one current arrangement alone. It contains the memory of a universe still in the process of organizing itself. That memory cannot be separated into perfectly clean pieces. Astronomers can estimate contributions from nearby clusters, distant concentrations, and broad voids. They can build simulations that reproduce much of the observed flow. They can compare one reconstruction with another and identify which features persist. But gravity does not label its sources. The local group does not carry a record showing how many kilometers per second came from Virgo, how many from the local void, or how many from Shapley. Those divisions are human ways of studying one continuous field. The field itself is seamless. Every mass contributes, though most contributions are tiny. Their combined effect forms the motion of groups, clusters, and larger regions. The closer structures usually act more strongly, while very massive distant structures add broader influences. Voids alter the balance because less matter lies in their direction. The resulting motion is not aimed along a perfect line. It bends through 3 dimensions, shaped by a landscape that has no visible surface. The Milky Way follows this path while also rotating, while the Sun circles within it, and while Earth moves around the Sun. Each motion continues without needing to cancel the others. The night sky appears steady because human senses are adapted to local changes, not to shared motion across millions of light years. A constellation does not reveal the local group's speed. A planet does not lean backward in its orbit. The atmosphere does not stream away from the moving Earth. Everything nearby is carried together. Only when astronomers compare our surroundings with the oldest observable light does the deeper movement emerge. The microwave background provides a frame broad enough to expose the drift of the local universe. Galaxy distances then turn that drift into a map. Clusters, filaments, and voids give the map its structure. The Great Attractor entered astronomy as a hidden answer. It became more useful when it stopped being one. The name now points toward a region, a scale, and a stage. In the effort to understand cosmic motion, it belongs to a larger account that includes Norma, Hydra Centaurus, Shapley, Laniakea, the local void, and the dipole repeller. None replaces the others. Each describes another part of the same uneven terrain. There may never be a final name large enough to contain the entire cause. Any survey has an edge. Any reconstruction has a chosen scale. Beyond each mapped volume lies more matter, more emptiness, and more history. A wider view may shift the apparent basin again, just as earlier maps shifted the focus from Virgo to the Great Attractor and then toward Shapley. Yet the absence of one final center does not leave the motion unexplained. It reveals the kind of universe we inhabit. Not a universe arranged around one hidden point, but one shaped by relationships across distance. Not a universe where galaxies travel toward fixed destinations, but one where matter responds continuously to a changing distribution of mass. The Milky Way is moving because the universe around it is uneven. That unevenness began as minute differences in the early cosmos. Gravity enlarged them. Time turned them into galaxies, clusters, filaments, and voids. Their arrangement now guides our local region through space. The same process that built the cosmic web is still carrying us within it. Far beyond the solar system, the local group continues its motion. Ahead lie dense structures, behind and beside it are regions with less matter. Around everything, space expands. The direction is real, but it is not a command. It is the present shape of a journey that has no single road. The galaxies keep moving through the dark between them.